Alright, so we just continuing on. We'll take the two values, the two coefficients in superposition, C1 and C3, and we will square them and then use them in the statistical formula, just ordinary statistics rather than quantum mechanics, the statistical formula to calculate the average. So simplifying things a bit, here's your superposed wave function, right, which consists of two wave functions. One, the solution to the STI, Schrodinger time-independent equation, when little n is 1. So that corresponds to the ground state energy wave function, right? And C1 is its coefficient. And similarly, psi n is 3, that's the next higher excited state, right? So that's the solution to the STI when n is 3. And the example we're talking about in the previous session is we have a superposition of only two states, two wave functions, psi of 1 and psi of 3. Okay. Now, so this talking is we're trying to reinforce the idea that using these coefficients here, interpreting them as probability amplitudes. In other words, you square them to get the probability of what you're talking about. In this case, we're talking about the probability of measuring the energy level at n is 1. So the ground state, in other words, the lowest energy level, or measuring it at for n is 3. So if the energy is 1, the ground state energy, from the theory of the infinite square well that we've done quite a few times, the lowest energy is just pi squared h bar squared over 8ma squared, right? And E3, well, it's just 9 times that. The general form, e to the en, you'll have n squared here, where n's an integer, positive integer, one of the countable numbers. One of the, well, just 1, 2, 3, okay, dot, dot, dot. Alright, so now it just becomes statistics. Now the average of anything is the probability of that anything times the value of the anything and summed over all possibilities. Okay, that's rather vague, but yeah, this is just from statistics. So it's just the sum of the probability of measuring the energy at the ith level, the ith value, times the energy itself, the ith energy. Now in this case we only have two different energy levels, E1 and E3. Okay, so from the if we interpret these coefficients now as probability amplitudes, so we have to square them to get the probabilities. So, so this then is the probability of measuring E1. This, when we square it, this is the probability of measuring at E3. So the average energy, the expectation value for your energy, will be the sum of these. So this is just the concrete example of this. All right. So what is C1 squared? Well, it's just a half squared, so that's a quarter. Okay. And the energy E1, well, you've got it here, so just plug in this value here. And C3 squared is root 3 over 2 squared, which is 3/4. So that's your C3 squared here. And the value E3, well, it's just this, so plug that in. And that works out to be 7 pi squared h bar squared, which is what we got before in the previous session. Now, I can see it, you can't see it. It's out of the range of the window of the camera. Okay, but that's what we got before. So that fits, right? So what we've done is reinforce the idea that we can interpret these coefficients here in the expansion of a superposed wave function that has been normalized. The wave function has to be normalized. That's important. Otherwise, if we square these numbers, we may get, if we square them and then sum them, we may get some number that's bigger than 1. Right? That doesn't make any sense if you're talking probabilities, and where the probability of some result has to be certain, and therefore the sum of all those squares has to be 1. Right? So you know, don't forget to normalize the superposed wave function that you're starting with. Otherwise, you know, all this talk of probability doesn't make any sense. Right? So I hope you see the logic of that. Right? Okay. Now I'll put a double bar here, meaning like a, you know, something significant is about to happen, and you could say what we're going to do now is we're at a kind of watershed. If you're not a native English speaker, what does that mean? Well, look at it as a kind of fork in the river, right? So your river's sort of flowing up this way, and then it splits, it forks. So the watershed, I can imagine a little shed, a little room, right at the fork. So you have to make a decision. Do you go left? Well, my left, or do you go right? My right. You have to make a decision. Like something important needs to be decided, or some kind of landmark, or something significant that's happening in the development of this course. And what it is, you know, we've been talking, you know, largely about wave functions a lot, and gradually, you know, last few lectures, we've been bit by bit retranslating or translating the language of wave functions into the language of vectors and vector spaces and so on. So from now on, we'll talk more and more in terms of vectors and vector spaces, and less until we don't talk anything at all about wave functions. So that's sort of, you know, what's being said here. So you can look on your vector type language as the primary way of talking about systems in quantum mechanics, and then you can represent those vectors in various ways. So instead of wave functions sort of being like primary, and then we translate from that into vectors, we can reverse the process and say, well, from now on we'll look on vectors as primary, you know, our main focus, and then wave functions become an example of these vectors. Okay, so in a sense you could say, instead of saying vectors a representation of wave functions, we can reverse it. You know, we can reverse it, and then say that the wave functions are representations of these vectors. And there may be other representations of these vectors. For example, matrix mechanics. If you look at the history of the development of quantum mechanics after Bohr, that's like the Bohr model, say 1913 or so, that was sort of a mishmash, a mix of new quantum thinking and old classical mechanical thinking. The real quantum mechanics really got going in the 1920s. And in fact it was Heisenberg who came out with a formulation of quantum mechanics that used matrices. He didn't realize it at the time because he didn't know enough basic algebra. I mean, abstract algebra as a concept was not very well developed, and certainly not well known amongst theoretical physicists of the time. You know, that came later. So he didn't really realize that what he was doing with his equations was in fact manipulating matrices. It took his supervisor, Born, in fact Max Born, to realize that Heisenberg was actually manipulating matrices. And so what Heisenberg was doing came to be known as matrix mechanics. Heisenberg didn't like that at first, but he sort of got used to it. Anyway, and then Schrödinger came along, I think about more or less a year later, and invented his wave mechanics, and that was hugely more popular because it was based on differential equations, and it was more visual, well, people thought initially at least, it was more visualizable. You know, this wave function had something to do with waves, you know, something that waved in the style of de Broglie. In fact, so for a while there was a bit of a controversy of which formalism, the matrix mechanics or the wave mechanics, you know, which of those two was you know, more accurate about, you know, in representing nature. How well did each of these two, on the surface of things, wildly different. You know, one was talking about matrices, and this other one was talking about waves and wave equations. Which of those two was a better model of nature? And it was Schrödinger himself, I think, ended up proving that the two were equivalent, or mathematically equivalent. He's able to show that you could map one into the other and vice versa. So effectively they're just two languages for the same thing. Anyway, so if you take your if you look on vectors now as your primary way of looking on quantum mechanics, the way you express the phenomena of quantum mechanics, then the wave functions would be one interpretation of these vectors, these state vectors, and matrix mechanics, you know, the matrix formulation would be an alternative representation. So now we can look on the primary way of looking at things as the vectors, and they can be represented in two different ways, at least, right? So one as wave functions, and the other as matrices, you know, the matrix formulation. And since those two are equivalent anyway, that makes sense, because they're both representations of your source, your basic formulation, and that is in terms of vectors, right? Okay. Right, so we're going to change terminology a bit, and now you probably noticed a bit in the past, for the last few sessions, I've been, it's been slipping out unintentionally, almost unconsciously. I'll be talking about, instead of talking wave functions, I'll use the term eigenstate, because I'm so used to it, and pretty soon you'll understand why, right? Because we're going to start talking in those terms as the norm, the new norm. All right. So we're going to change terminology a little bit now. So instead of talking wave function, we'll talk like a vector. Now it's a state vector. Now, what do you mean by a state? Well, I've done this several times. The state is a kind of description of what's going on. Like the wave function here is a state, because it, you know, it tells you something about your quantum system. You know, what the wave functions are and what these probability amplitudes are. So this whole thing is a kind of state. It's a kind of description of your physical system. Tells you about the system, like